Welcome everybody for joining us today for the Double Asteroid Redirection Test or DART mission, Preparing for Impact. We are broadcasting from the NASA Johnson Space Center in Houston, Texas. And we really want to welcome all the participants that we have with us today. We've got students in grades 4 through 12 plus, formal and informal educators from 24 different states across our nation. So we are so glad to have all of you with us here today. We're also really glad that we have our featured speaker and our event facilitators, but our featured speaker, Paul, is one very busy individual, especially now as we're getting close to the DART impact, which he will talk about with us here in a few minutes. So we're certainly very thankful for all of you to be here, and we look forward to having Paul start sharing a little bit about the DART mission. And also, Paul, if you'll start with a little bit about yourself as well.
Okay, great. Well, hello everybody. I'm really excited to be here with you and share about the DART mission, and it's an exciting mission. A little bit about me. I'm actually from Canada. I'm Canadian. I moved down to NASA Johnson Space Center to start work here back in 2004 and have been here ever since. My title is Chief Scientist for Small Body Exploration. What that means is basically I study asteroids and comets. Asteroids, big rocks in space. They're my specialty, and it's my passion and what I really like to learn about. So think of me as sort of a planetary geologist, but like a geologist on Earth, I don't use a magnifying glass or a rock hammer to look at my rocks. I have to use big telescopes and spacecraft to look at my rocks because they're very, very far away and they move very fast. So I'm going to stop sharing my video. I'm going to share the content here and we'll get into the actual presentation. Yes. So this takes a big team to put a mission together like this. So this is a DART investigation team. These are all the institutions and countries. There's over 230 people who work on the DART team. And this is all because planetary defense is an international effort, right? We need international cooperation for an international issue. So we have over 230 members from over 100 institutions and 27 countries. So I just wanted to make sure that people know that this is not just me doing this mission. This is a lot of people all over the world. Okay, this has no sound, but I wanted to give you an idea of what happened and why we care about planetary defense. Back in 2013, over Chelyabinsk, Russia, a significant meteor came in about 20 meters across, a bit bigger than a school bus size, came in at high speed and exploded over Russia. And it released a lot of energy, 20 to 30 times more energy than the atomic bombs that were dropped in World War II. You can see the fireball going across the sky there from video cameras. Lots and lots of damage over the area, lots of windows broken, and several people, about 1,600 people were hurt actually. 100 people were hospitalized, but 1,600 people were hurt. So this was a big day for us. This was something that caught us by surprise and certainly got our attention.
И сгорел там, да? No.
That's what happened. They were looking up at the sky and they saw the contrail, and all of a sudden that blast, that shockwave hit them, right? So they're pretty frightened. So here's some more videos. Again, no sound on these, but you can see the shockwave hits and all the windows blow out, or a lot of the windows blow out. So these are cameras that are just set up, and this was wintertime in Russia, so a little bit cold. So when they have all the windows blow up, that's a problem. Watch what happens here. There's this, what happens to the ceiling and these people. Those glass ceilings cave in this warehouse. And then watch what happens here. They see the flash and they're looking up at the sky at that big contrail, and all of a sudden the shockwave hits and blows people back away from the windows. So again, they didn't know what was going on. They didn't realize it was an asteroid impact. They thought there was something else. Watch what happens to this door. It blows out, blows in, I should say, from the shock wave hitting. So kind of a very, very scary. Um, Again, watch what happens to these people. They're starting their morning. They don't know about the asteroid impact. They're near the window, and they think, you know, they're not sure what's going on, but something bad's happening, so they run away. So these are all these type of things that happened. Again, you can see this in a classroom. Children getting ready in the morning, and the windows blow in, and lots of explosions. So this is what where the last piece or the final piece to make it to the ground from that asteroid, this big meteor that came in, and it actually punched a hole in the ice, and they actually recovered quite a bit of it from the hole. They had to go down and dig it out and get it. So that was an interesting day, February 15th, 2013 in Chelyabinsk, Russia. We were very busy trying to figure out what happened, and like I said, it got people's attention. So I wanted to share with you, this is a slide of basically what we see from satellites looking down on Earth. They're looking down at Earth for other things, but in the process of doing so, they see lots of what we call high altitude explosions from asteroids and comets hitting our planet. And you can see these dots, they hit everywhere all over the Earth, right? You can see here's North America, South America, Africa, Europe, Australia, Antarctica. And it doesn't matter where you are on the Earth, these asteroids can come in and hit in any type of direction in any location. The size of the dots corresponds to how big and how much energy those asteroids release when they hit the upper atmosphere and explode. So fortunately for us, a lot of these represent very small asteroids, only maybe 1 or 2 meters across, right? Maybe things as big as a basketball or beach ball, maybe a bit bigger than that. The Chelyabinsk one, though, was this. This was Chelyabinsk, and it was a big one, and you can see that was a 20-meter object, like I said, and it released lots and lots of energy. So these things happen all the time. This is information that we've gathered since 1988 up until just September 22. So we're constantly getting hit over time. Okay. All right. I have a question. This is for you guys. All right. So approximately how many asteroids are in our solar system? You have three choices. Are there hundreds, thousands, or millions? Take your best bet and put it in the chat. And then maybe also think about what things do you think make an asteroid potentially dangerous to Earth? And Paige, I'll turn it over to you.
Great. So as you're putting your answers in, and I'm seeing a lot of very similar answers, but I won't spoil it for everyone. So put those answers in. But then additionally, that what do you think makes an asteroid potentially dangerous to Earth? That would be a great, we're really interested to see the type of input and thinking you all think out there. And again, if you want to start your answer with your school or org name, then we can kind of give you a shout out. So we'll get back to the approximately how many, because I do see most folks are in alignment with what they're saying. But then we have Upper Darby. They're saying the speed, size, and location, Upper Darby High School, they think that would sort of pertain to why or make an asteroid potentially dangerous to Earth. Massabesic Middle School says the diameter and the impactor size or the impact size would certainly make an asteroid dangerous, as well as the sound and the sound barrier. OLPH says the proximity of asteroids and size of asteroids would make it perhaps more dangerous. Another group says the speed at which the asteroid hits, as well as its size. Someone actually mentions that there could be a danger of a tsunami or cloud and or weather change from an asteroid impact. Duxbury Senior Center says the speed it travels, the size, and perhaps even the composition. St. Dominique Academy says the velocity and size, and even UTEP Teacher Prep adds in temperature. So size, speed, temperature. And Ronan Elementary says, what makes them dangerous? Well, if they could kill people, that would make them dangerous. And KWH Elementary in Montana says it would be dangerous if an asteroid actually hit a city. So the majority, if not everyone, Paul, says there's probably millions of asteroids, and mostly size, speed, and location of impact. So what do you think, Paul? Back to you.
That's awesome, guys. You guys are right on. Yeah, millions and millions of asteroids. We'll get into it a little bit more. And there's lots of things, aspects like obviously their size, their velocity, what they're made of. All those things, like you said, are exactly right, come into play to make an asteroid potentially dangerous to the Earth. So this is some of the things that I work on, obviously, to try and make sure that, we don't have a bad day. We don't want an asteroid to come in, a big asteroid to come in and hit us. I think you guys may be familiar with how what happened to the dinosaurs 66 million years ago, right? They didn't have a space program and they were taken out by an asteroid. So we have a space program and we want to make sure that that doesn't happen to us. So let's get into a little bit more background on asteroids, but I think you pretty much all got this, but just to say, this is how it's all going to go. So here we are at Earth. Here's our happy planet. And you can see where the Earth is. The yellow dot is the sun. There's Mercury, Venus, Earth. The red dot there is Mars. We're looking down on the solar system. The asteroids are marked, and Jupiter is in that orbit outside of the asteroid belt. And asteroids are basically just leftovers from planet formation. They're the rocky bits that didn't get incorporated into the sun or the other planets, right? And you're right, there are millions of asteroids, but even with all those millions, there's not enough of them, the mass of them, to make up what we see in our moon, right? So here I show you on the lower right, there's a plot of the inner solar system, and you can see this little dot here. Hopefully you can see my cursor. That is the Earth, and you see all those red dots, those are near-Earth asteroids. So we live in a constant swarm of near-Earth asteroids, right? That could give us a bad day one day. Right now we're good, we don't see anything happening, but we just want to be ready. Again, we don't want to end up like the dinosaurs. So here's our Earth, here's the moon, and here's Ceres. Ceres used to be, it was referred to as the biggest asteroid in the main belt. It's now reclassified as a dwarf planet. And so I'm just going to zoom in here now and give you a sense of how big some of these asteroids can be. So here's Ceres on the right. Here's 4 Vesta on the left, right? Here's Vesta over here. And this is the biggest asteroid in the asteroid belt. And then all these other asteroids here are all asteroids in the main belt that we've visited with spacecraft. Like all these images I'm showing you are images from spacecraft that we've sent out to visit them. This little guy down here is a near-Earth asteroid. You can't see it. It's a small dot, but to scale, you won't be able to see it. So I'm going to now take you to 2 asteroids that we recently visited. These are near-Earth asteroids, and these are both potentially hazardous. And these were visited by NASA and the Japanese Aerospace Exploration Agency. So on the left, we have Ryugu, asteroid Ryugu. It was visited by the Japanese spacecraft called Hayabusa 2. And on the right, we have asteroid Bennu, which was visited by the NASA spacecraft OSIRIS-REx. So both of these asteroids are potentially hazardous. Both of these asteroids are very interesting scientifically because they can tell us a lot about the early solar system. And both of these asteroids actually contain water. So that's really important to understand to try and figure out, how maybe they played a role in delivering Earth's water early on. There's some ideas that these asteroids played an important part of life formation on Earth. One of the other neat things I should tell you is we have pieces of Ryugu on Earth. In fact, we have pieces of Ryugu back here at Johnson Space Center, and we're going to get pieces of Bennu back here next year. The spacecraft returns samples of Bennu in about a year's time, and it's going to land in Utah, and then we'll have those pieces here at Johnson Space Center. So it's a very exciting time. But these asteroids are the type of asteroids that could potentially give us a bad day. These guys aren't going to give us a bad day anytime soon, but these are just representative of bigger things that we have to watch out for. Okay, so here's how it looks in terms of the numbers. Okay, so in the top part, you have asteroid size, and then how often they may hit, and then the impact damage, the numbers, and the percent discovered. And one of the things I want to show you is here's the really big guys up here, right? The things that are 10,000 meters or 10 kilometers in diameter. This is the type of thing that wiped out the dinosaurs 65 million years ago. There's about 4 of these. We know where every one of these guys is, right? So we're safe from them. For things that are a kilometer and up, we're doing really, really well. We've got 95% known. So this blue part is the things that we know about. The gray part is not. So we've got about 5% left to find of these guys. So we're feeling pretty good, but we can't let down our guard because, even a 1 kilometer diameter asteroid could give us a really bad day. So basically, can have a really bad day. We're doing pretty well on these bigger ones, right? The bigger guys, and we want to concentrate on those first because those are the ones that, like I said, can give you a really bad day globally over the Earth. So we concentrate on these guys first. If you're really large and you're basically easier to find, the smaller guys are the ones that are harder to find. And as you note here, we still have a lot more work to do. So it's not to say that we're not too worried about these small guys. We are, but we have to work harder to try and find them because they're small, they move fast, and they're dark, right? They're not like the sun that gives off their own light. They're like the moon. It's reflected sunlight. And some of these asteroids are darker than coal. So they can be really, really, really dark and really hard to find. So we've got lots and lots of asteroids. Notice the numbers here. You guys were right in terms of the millions, but we have lots of work to do. So this is a slide that I also like to refer to as job security for me, because I have lots of work left to do because there's lots of asteroids to locate and make sure that we don't have a bad day. All right, so I work for planetary defense. NASA, we have a planetary defense program, and we have lots of aspects of the program. So the first thing you got to do is you got to search, detect, and track, right? You want to be able to find out where these things are. You want to characterize them, figure out what they're like, what they're made of. You got to plan and coordinate what you're going to do about them, and then you've got to try and deal with them. So it goes like this. Find the hazards, find the dangerous asteroids, and find them early. Defend against them, and make sure you can protect the Earth, protect the people. And so that's why DART is really important, right? So DART is basically a NASA mission, like I said, and it's out of the Planetary Defense Coordination Office. DART is targeting a binary system. So a binary system, believe it or not, sometimes asteroids come in pairs, sometimes even triples. Triples are really rare, but in pairs. So when we have a paired asteroid together, one asteroid orbiting around another, it's called a binary, right? So this larger asteroid, the smaller one is orbiting around it. We are going to target, this is the DART spacecraft, it's going to hit this small asteroid called Dimorphos, which orbits around Didymos. Notice that there's this little spacecraft flying behind DART, that's LiCiCube. When DART smashes into Dimorphos, LiCiCube is going to watch what happens and report back to Earth. So again, DART is targeting a binary asteroid system, but we're hitting the smaller one, and this asteroid is about 160 meters in diameter. Okay, and this is just to give you an idea of how big 160 meters is. So here's Dimorphos, 160 meters. Here's the DART spacecraft, 19 meters, right? Much smaller, bit bigger than a bus, smaller than the Arc de Triomphe or the Statue of Liberty. Dimorphos is in here, probably about the same size, maybe a little bigger than the Great Pyramids in Egypt. Didymos over here is really big, right? Really big. So here's the skyscraper, the One World Trade Center in New York City, and it's bigger than that. So it's just to give you a sense of scale of how big these asteroids can be. All right, here's another question for you guys, okay? So what do you think the DART team anticipates will happen during the impact? So include your reasoning with your answer. So you have a choice. The little asteroid will completely break up. So Dimorphos will completely break up. The asteroid will be moved slightly, or the small asteroid Dimorphos will be pushed away to orbit a different but nearby asteroid. Paige, over to you.
As you are putting your answers in the chat, again, if you're looking, we'd love to give you a shout out. So start with your school or org name and give us some reasoning. Any thoughts on why you're choosing A, B, or C? So we'll see what answers come in. I do see some thoughts in terms of A, B's, or C's, but we'll wait to see the type of reasoning if you can put in some reasoning with your answers. So Shaker Heights says B because it's too small to do A or C. One of our solar system ambassadors says moved slightly because kinetic energy is in action and only move it a little bit. Massabesic Middle School from Maine says B, just not enough to change the orbit. Mansano Middle School in Brownsville also agrees with B. We'll hope to get a little bit of reasoning why. Duxbury says B also because the size of the craft is not big enough to cause anything larger in terms of the changes. Upper Darby also says B. UTEP Teacher Prep says B because DART is again much smaller than the target asteroid. St. Dominique Academy says we don't think the force will be powerful enough to break it up, so we think B or potentially C, but not A. San Benito High School says B because there's not enough force to do A or C. Our Lady of Perpetual Help says they think possibly A because it would be launched with enough force to break it. So a lot of kinetic energy. And Mansano Middle School says it's too large to be destroyed in one blast, meaning the asteroid. So some very interesting thoughts. And the reasoning becomes, such an important aspect of answering any question. So Paul, mostly B's, and you heard some of those reasonings. What do you think?
That's great, guys. Actually, we're not exactly sure what will happen. That's one of the reasons why we're doing this test. Remember, this is a test. But we think B is probably more likely, right? Every time we go to see an asteroid up close and personal, we are surprised by something, right? And we've done that. I've been on several spacecraft missions, and we think we have a good idea of what it's like, and then we get there, and they're like, "Holy cow, this is completely different than what we saw or what we thought." And so we think it's going to be B, but we really don't know. I think the chance of C or A are unlikely, but we'll see. We'll see. But B is the way bet. I think that's what we're going to lean on, and we'll see in a few days' time what actually happens. Okay, so here's a little bit more detail about the mission, right? So I already told you we're targeting this binary asteroid system. It's called the Didymos system because the big asteroid is Didymos. The small one is Dimorphos. We want to measure the change. We think that we're not going to break it up. We think we're not going to push it out of the orbit and make it go away and orbit another asteroid. We think we're going to change its motion slightly, so change the orbit around Didymos, right? So if that orbit changes slightly, we can measure this change from Earth. So that's what we have here. We're going to have Earth-based observations. They're going to look at the orbit. We're characterizing the orbit now, and then we'll see after the impact if there's any change. So here's DART again, 19 meters across with its solar panels here. The main spacecraft here is probably the size of a large freezer you might have like at home. I'll show you some images of the spacecraft up close and personal later on. It's traveling really fast, 14,000 miles per hour when it hits. So it's going to hit, and this is the exact time. We know this because we have really accurate measurements of how fast DART is moving with respect to Dimorphos. So September 26th at 7:14 p.m. Eastern Daylight Time, stay tuned because that's when we're going to hit our our asteroid. Okay, and then like I said, we have the LiCiCube, this little free flyer spacecraft that was deployed after DART, that will after DART was launched and just recently deployed, actually just a couple of days ago from DART. You'll see that in an animation, and it will monitor and watch what happens as DART slams into Dimorphos. Okay, so one of the things is we think Dimorphos is going to be moved slightly, but we don't know by how much, right? And a lot of it depends on what the asteroid is made of and how it reacts to DART impact. So in the best case, we think we have an impact and a small momentum enhancement. In other words, you push it, there's not a lot of big crater, there's not a lot of debris formed, and so you just get a slight movement, right? Slight movement. The other case is, hey, we hit it a bit the same energy, but because of the asteroid's composition and how it's put together, there's a lot of debris. There's a lot more debris thrown up. And that debris acts as like a little thruster, so you get more push this way, right? So maybe the efficiency is a little bit higher in terms of the impact and how far we move it. And then if we get a real large amount of debris, or rejecta as we call it, because the asteroid may be very weak, then we can get a really significant push. So these are some ideas, but we really don't know how Dimorphos will react to DART, and that's why we're doing the test. It's sort of like, you know, every time you want to do something, whether you're playing for sports or you're playing a musical instrument or anything, you practice, and that's what we're doing. We're practicing planetary defense because we want to make sure that we get this right so that if we do have to do this for real, we know what we're going to do and we'll be successful. Okay, so here's the ideal time. So here's an animation I've got. Didymos is in the orbit there. DART is launched from Earth, and you can see they're going to meet up and eventually going to impact. This is actually a relatively short mission. DART was launched on the 24th of November in 2021. And then you'll see it's going to hit here in September 26, 2022. So it's a short mission, but actually a very, very important mission. So that just gives you an idea of sort of the overall geometry of how things go when we launch and then impact this particular asteroid. And the reason why it's a good time is because Didymos and Dimorphos are very close to the Earth at the time of impact. See how close they are here? So we have a better chance of seeing what happens from the ground. It's not way far away on the other side of the sun. We get to observe what happens with our telescopes. So that's really important. So again, here's an animation. So we're observing from Earth here on our ground-based observations, you see, and we monitor Dimorphos orbiting Didymos, and there's the original orbit that's mapped out, as you can see. And then all of a sudden, DART comes along and launches LiCiCube. So there's the impact from DART. LiCiCube flies by, but watches, and then reports back all the information, all the data that it took, all the pictures that it took. And then hopefully we've changed the orbit of Dimorphos. So that new orbit, you can see it's much different than what it was before. We've actually slowed Dimorphos down and we've changed the orbit. Even if we change an orbit just by a little bit, you know, we're hoping for 1%, but that will be able to tell a lot over time with our ground-based telescopes. We're really good at measuring things. So even that small little change we'll be able to see really, really easily. And this is how we do it. This is why this particular asteroid, the binary asteroids, are so fun. So one of the things I'm showing here is on this axis, you'll see here's brightness, how bright the signal is from both asteroids over time, and you'll see these dips. So when Dimorphos goes behind Didymos, there's a dip. The light is lessened because we're not getting as much light. Both asteroids are in light and reflecting back to us, so it's big. Now Dimorphos goes in front and eclipses, and now it goes behind, and there's a dip. Now it comes out, and we're back up to full brightness. And then it will go in front, a dip, shadow, eclipse, and then back up to full brightness. So what we're doing is we are measuring the normal orbit period. So the timing of these dips, we can measure very accurately. When the orbit changes, the timing of these dips will shift. So this dip here, for example, will be shifted this way. It may be shifted shorter. And we can measure that and then figure out how hard and how efficient we are in changing the orbit of Dimorphos, and that helps us understand how we can deflect a dangerous asteroid in the future, how hard we have to hit it, and where. Okay, so remember I said there's lots of people all over the world that are working on this mission, right? So here's an example of all the telescopes that are looking at Dimorphos and Didymos. Okay, we have the United States, we have United States and mainland United States. We also have Hawaii, we have South America, Africa, Europe. We have some assets in Asia, Australia, even in Antarctica. We have a telescope that is looking at. We also have telescopes in space. Here's the Hubble Space Telescope, the James Webb Space Telescope. Also, the Lucy spacecraft on its way to Jupiter is going to look back and look and see what happens when DART slams into Dimorphos. So we have lots and lots of telescopes that are observing, and we'll do this constantly. We're observing right now we've started last year, and we're going to be going through into 2023 to see what happens with Dimorphos. This is what it looks like. I don't know if you guys can pick this out, but this is some observations that one of my colleagues, one of my friends made from the Lowell Observatory. This is just, in July, just a few months ago. And here's the asteroid. You can see it move. So this is Didymos. And what he's doing here is, in this camera, just monitoring the motion, but you can put an instrument and measure the change in brightness. So he can actually figure out the rotation period of that eclipse, those dips, remember I showed you on the light curve, as we call it, and get the timing. So this is what all these telescopes are going to do. They're very sensitive, and they can measure those very, very subtle changes in brightness of the asteroid as it moves through. So that's what we're going to be doing for the next several months after the impact to try and measure the change in orbit. Okay, so here's the DART spacecraft up close and personal. This is an artist's picture of it. One of the things I want to show you is this is Draco. Draco is our eyes. This is the only instrument that we have on the spacecraft. And it's basically a telescope camera. Draco stands for Didymos Reconnaissance and Asteroid Camera for OpNav, optical navigation. So this camera is used to find Didymos, to help characterize it, and then help guide the spacecraft to impact it. And this is about an hour out. This is what Draco would see. So you see Didymos is the bigger asteroid. It's now honing in, aiming at Dimorphos. And you can see as it zooms in, this is really fast, right? The spacecraft's moving really fast. And it doesn't take long for it to come up on Dimorphos and then hit it. So here we are. We're still thousands of kilometers away, but we're only 4 minutes away from impact. And this is probably the last image that we would see. From maybe about 9 kilometers out, we would get an image of the surface right before the signal goes dead as the spacecraft smashes into the asteroid. Okay, so this is an animation. This is what it would look like if you were standing on Dimorphos. You're looking at your big friend Didymos over there. Everything's fine. What a nice day it is. You're looking at the stars. It's a beautiful night, starry sky. You're enjoying the view, and then you start to see something, and you're not exactly sure what it is, but it's getting closer and closer and closer and closer, and you're like, "Hey, that's a spacecraft," and it smashes into the asteroid. Okay, so this is what DART looked like before it got loaded into the rocket. Okay, so these are the roll-up solar arrays before they were deployed. So these are tightly rolled up. There's one on this side and one on the other side. The engine, one of the engines for DART is up here. The camera, Draco, is down here. And this little boxing, so this is already deployed, and we've got signal from LichieCube. It's flying along behind DART and operating really, really well. So this is just to give you a sense of scale. Like I said, it's about the size of a big freezer. Here's the rocket it rolled on. So this is the nose cone of the rocket, or what we call the payload fairing. That's this bit up here. Here's a person for scale. Here's DART in the nose cone of the rocket right before it's sealed up. And this is the size of the rocket. So this is a SpaceX Falcon 9 rocket, really big rocket. And it was launched from Vandenberg Space Force Base out in California. So it was a great night. It was a nighttime launch. I was there. Tremendous view. This is what it looked like going through the clouds and the fog, and it was actually spectacular. And here
10,
is
9,
launch.
8, 7, 6, 5, 4, 3, 2, 1. And liftoff of the Falcon 9 and DART on NASA's first planetary defense test to intentionally crash into an asteroid.
So we were really happy. We got a really great launch and a really great trajectory from the Falcon 9, and everything was good.
The job of Falcon 9 was to get
This shows the
DART on its
DART
way to the
spacecraft
Dynamo
separation.
system. At this point, we've gotten enough velocity, enough speed to send DART off towards the Dynamo system. And right now, we're in range of the ground station, so we can get all the data from, and so we can make sure we can actually capture the separation event.
Confirmed.
And we just heard the call out for spacecraft separation. You can see the video of the DART spacecraft heading on its way to the Dynamo system.
What a spectacular view of DART.
Yep.
Just floating away from the Falcon 9 second stage.
Yeah, it was a great video. So you get to see this is the Draco camera. This is the antenna to communicate back where the solar arrays are still not deployed. They're full up. So it was a great deployment. All right, question for you guys. Earth is not currently at risk of being impacted by a large asteroid. So that's something I should really stress to you guys, right? I sleep pretty well at night. One of my jobs is to help protect the Earth from asteroids. I'm pretty happy about how things go for right now, but we still have to be careful, right? So why is the DART mission important? And Paige, I'll turn it over to you to get the response from the participants.
So we want to hear from you and your thoughts on, if Earth is not currently at risk, why is a mission like DART important? So think about that. And again, put your school name in there first if you can, so we can give you a shout out. And this might require a little bit of thinking because this is a bit of a higher level kind of question. But we've got responses, Paul, coming in. Duxbury Senior Center says we need a plan. San Benito High School says to protect us from possible future risk. UTEP mentions that in case we have a potential repeat of the event like that occurred in Russia. One of our solar system ambassadors says to help deflecting smaller asteroids. Upper Darby High School says to be prepared for the worst in case we are ever at risk in the future. Shaker Heights High School mentions it's the asteroids we haven't discovered yet that we need to be prepared for. Alfred Elementary says it's important to be ready for the future possible tragedies for Earth or other planets. Another solar system ambassador says the change in orbit will determine what type of impact energy will be required to deflect an asteroid incoming to Earth, perhaps in the future. Massabesic Middle School from Maine says in the future, we will know how to change the trajectory of an asteroid. Now, St. Dominique Academy says we might need defense in the future. We don't want to get surprised. St. Lawrence Middle School says the potential of asteroids coming to Earth to try out this type of response. And then we have Our Lady of Perpetual Help says, in case a large asteroid comes in close in the future. So we have some people that really have their thinking caps on there, Paul. What do you think of these types of responses?
Those are some great responses, right? That's exactly what we're doing. We're trying to get ready just in case, right? Right now we're not at risk, but as that slide and some of the things I showed you, small asteroids do hit us all the time. We just want to make sure that we don't get hit by a big one, and we don't know exactly where, we don't know exactly when. We also don't know exactly how big. So we just got to be ready. And so that's why the DART mission is really important. Like I said, it's a test for planetary defense. We're practicing helping protect the Earth from an asteroid impact. And one of the things that I did say, I think I saw someone chat move through. Someone mentioned that it might be important later on if we're on the moon or Mars, and that's exactly right. One of the things that's planetary defense. Our primary planet that we have to protect is Earth, but if we have people living elsewhere on the moon or Mars, we need to think about also protecting them out there, and so that's why we try and do all these things. So those are some great answers and great responses. Okay, so here's a slide for you guys. If you want to be a planetary defender, please join me and my team, right? So there's a couple of websites I put on here. There's lots of social media. I'll leave this up for a bit so people can maybe capture it. And Paige will put it in a follow-up email to your teachers and other people that are running these meetings. But basically, you can become a planetary defender. You can join the DART team as we go and about to smash into Dimorphos. So all of these things are going to be great. Please follow along. And there's lots of resources out there and lots of fun things to do as well. For example, we have a whole outreach webpage where you can get information on how to print 3D models of not only the DART spacecraft, but also the Didymos and Dimorphos system. You can do an augmented reality experience. We have models, toy bricks, models that you can build. And then we also have information on how to host a watch party where you can actually watch the event in real time as it happens. So lots of exciting things for you guys to think about. And hopefully you'll join us and maybe even have a watch party on the night, Monday night, September 26th. So here's a video. I'm just going to let this play. This is a great video. It just sums up everything about the DART mission. And that's it. So feel free to follow along. The live coverage starts on NASA TV and NASA YouTube and Facebook, Twitter, starting live coverage at 6 p.m. Eastern Daylight Time, going through 7:30. Again, the impact is scheduled for 7:14 p.m. Eastern Daylight. Pause here, and I will turn on my video and see if there are any other questions if we have time.
Absolutely, Paul, and absolutely incredible. In the chat, folks are indicating how awesome this presentation was. And so we very much appreciate you generating not only the knowledge, but the excitement about what is to come on September 26th and all that has led up to it. So fantastic. And we do have questions. And for folks that have been thinking about questions they might have, if you haven't put your questions in the Q&A area yet, feel free to put them in and we'll try to have Paul answer as many questions as possible. So Paul, I'm going to start with this question that came
Sure.
in. Will the DART mission be able to determine anything about the composition of either of the asteroids?
Yeah, well, actually, the ground-based telescopes, we have an idea of what the composition of the main big asteroid is, Didymos, right? The smaller one is a little bit too small to get a signal from. We think it's related just because of the way binary asteroids form. So we think it's actually a piece of Didymos that's been spun off and then captured in orbit. Um, but in terms of the spacecraft itself, it won't determine per se the actual composition. We'll get some hints on some of the internal structure and how it's all put together and what the geology is like. But in terms of the actual composition, whether it's a certain type of meteorite, certain type of minerals, that doesn't come necessarily from DART, but we get that a lot from the ground-based observations, which we're doing. I should mention there's a follow-up mission that actually will be able to determine the compositions of these asteroids up close and personal and actually look at the crater that we made afterwards. I didn't have time to go into it today, but there's a European Space Agency mission, the ESA mission called Hera, which is going to launch in about a couple years, and it will get to DART in the year 2027. That spacecraft is going to go and rendezvous with the Didymos system and observe Didymos and Dimorphos, and it will have instruments to analyze the composition of Dimorphos specifically and look at the crater and see if there's any differences in the surface of Dimorphos versus the depths. As you punch in, if you make a crater, you may get some hints of what the interior of the asteroid is like. And so that's something that they're really interested in doing. So you may have to wait a little bit longer, maybe a few more years before we get that information on the actual composition of Dimorphos. I hope that answers the question.
And that's a great response and really great information because it brings up sort of an aspect associated with what you showed early in your presentation as well as what you touched upon here, and that's international participation. So is there like any specific group or is it always an international participation for missions like this now and in the future, or would that be like Space Force or just NASA or any individual country?
Yeah, so it's a good question, Paige. So this is an international effort, defending the planet. It's just more than just the United States. It's Europe, it's Asia. There are a lot of countries, and the United Nations is also interested in this. So we have several space agencies from around the world that work on this. I will say that NASA takes the lead. We are the leaders in planetary defense, but we have some key partners. Specifically, we have the European Space Agency. They're our biggest partner in planetary defense. Like I said, they're providing the Hera mission and going to investigate Dimorphos after the DART impact. They have some other plans for some of the other things they may be doing to help us with planetary defense. But we also have some input and help from the Japanese, the Russians, and a few other countries around the world. We're just starting to get really well organized, but we're hoping that with the DART mission and the Hera mission, we'll have a lot more missions and it will be much more an international effort as we move forward to help protect the planet.
Excellent. Well, thank you for the question and thank you for the answer, Paul. Now, this question I think comes from K. William Harvey Elementary in Montana, and they are wondering, can you actually land a spacecraft on an asteroid?
That's a great question. And yes, we can. We've done it in the past. So one of the first missions I was involved with was the Near Shoemaker mission, and that was to asteroid Eros. And at the end of the mission, we actually landed the spacecraft on the asteroid. You have to do it very carefully because there's not a lot of gravity. We've also had experience with other asteroids where we've briefly touched down, landed, if you will, for a brief moment on the asteroid. So this is with the Hayabusa 2 and OSIRIS-REx missions where we wanted to touch down briefly and get a sample from the asteroid. Hera, like I mentioned, the European Space Agency mission, one of their plans right at the end of the mission, when they've done everything else and they're finished investigating and studying the asteroids, they're going to land. And their plan is to land on either Didymos or Dimorphos, but their plan at the end of the mission, they're going to try and land. And hopefully we'll learn a lot about how that works. It has to be done very carefully because, like I said, there's a lot of gravity. You come in too fast and you either crash and break up your spacecraft, so it's not a landing, it's a crash landing, or you come in too fast, you survive, but then you bounce off and then can't come back to the asteroid. So you have to do it very, very carefully, but it is possible.
Yeah, and that was a very interesting question. And, with so many asteroids out there, there's so many interesting things to learn about each and every one of them. But with millions of them out there, we're probably not going to get to learn about each and every one of them. But these missions like this are certainly extremely fascinating and give us a whole lot of knowledge. So here's a question from UTEP. They're wondering, are you worried at all about space junk or other repercussions of crashing a spacecraft into an asteroid and or setting the asteroid sort of off its orbit?
Right. So we get this question a lot with the DART impact and what we're doing. So one of the reasons we picked this particular asteroid is this is a very safe asteroid. Anything we do to it, it's not going to make it dangerous. It's not going to change its orbit all of a sudden to crash into the Earth. Um, this is one of the reasons why we picked it. And even though the DART spacecraft is moving very fast, the amount of energy that it's giving to Dimorphos is still relatively small compared to the rest of the mass of the asteroid, how big it is. So um, there's nothing bad that is going to happen. We're not worried about changing the orbit or creating a whole bunch of debris that will eventually come back and give Earth a bad day. It's one of the reasons we picked about this particular asteroid. So I'm very confident that we're going to do a successful test, but there's no danger to the Earth later on. Yeah.
Again, another great question that that the folks have asked. Now, here's one that came in early on, but I want to just sort of touch on a couple of things because this individual from Duxbury Senior Center mentioned that movies show huge number of asteroids in the asteroid belt, and so if a craft goes into the asteroid belt area, does it have to like dodge asteroids as it moves
Right.
through, or could the craft possibly not even see other asteroids or be in danger? So can you talk to that a little bit?
Yeah, so I think people have seen lots of movies, Star Wars and a few others, where you have um, spaceships flying in and around and dodging asteroids and weaving in and out, and all these asteroids are really close together. And that's not how it is at all. You have to keep in mind that asteroids are relatively small compared to the vastness of space. Space is huge, it's big. Um, for example, if you're in the main asteroid belt, right? If you stood on an asteroid in the asteroid belt, you would still need binoculars or a small telescope to see the next closest asteroid to you. It's really, really big, and it's not like a packed, dense cloud that you see in the movies. When I showed you the animations, I had to make those dots, when you saw the animation of the inner solar system with all the green and red dots moving around, I had to make those dots exceptionally big in order for you to see them. If I put everything to scale, you wouldn't really see too much. So space is really big, asteroids are small. There's not this wall of material that, in the movies. We've sent many, many spacecraft through the asteroid belt with no problem. So yeah, hope that answers the question.
Excellent. Thank you, Paul. And I know we're close. Actually, we are at the bottom of the hour, but I'm going to ask one additional question unless something comes in before we officially bring this to a close. And hopefully, folks can hang on for another couple of quick minutes. So, Alfred Elementary has actually asked, asteroids, could they have actually contributed to the formation of glaciers or even bringing water to Earth?
Yeah, it's a great question. So, um, there are some evidence to suggest that asteroids and comets, but mainly asteroids, may have contributed a lot of water and what we call organic molecules to the early Earth, right? And they may have helped form the oceans that we see today, and also how helped influence how life has evolved on our planet. So not only just from the standpoint of, having big asteroids come in and wiping out life on Earth, like what happened to the dinosaurs and several other species 65 million years ago, 65, 66 million years ago, but they could have also brought a lot of useful materials such as water and organic molecules. So remember those two asteroids I showed you, Ryugu and Bennu. The reasons that they were picked for the spacecraft missions of Hayabusa 2 and OSIRIS-REx were because those are scientifically very interesting. From our ground-based observations, we had hints that they looked like they could be um, contain water, could contain organic material. And we have meteorites on Earth that have water inside them, trapped inside the rock, and they're made up of organic material as well. But we didn't know exactly where those type of meteorites came from. So we know they came from an asteroid, but we didn't know which ones per se. So uh, Ryugu and Bennu are these two very dark, what we call carbonaceous type asteroids, and we now know for certain, because we've got samples of Ryugu back in the lab right now, that there's water or organics on Ryugu, right? So Bennu, we haven't got the samples yet, but the way to bet is it looks like that will also be a water-rich, organic-rich asteroid. So yes, these types of asteroids had probably a vital role to play in how the Earth evolved over time, both in terms of the oceans and the water that they brought, but also the organic material that helped influence how life formed on our planet.
And such an important and interesting topic. And if you think about it as well, would you also say, Paul, that asteroids could have potentially brought water and organics to Mars as well as other worlds in our solar system?
Yeah, I mean, that's a great question. I mean, it's not just, they don't just do it to Earth, they do it everywhere, right? So keep in mind the asteroids and the asteroid belt, you have material that moves inward, right? But you can also get material that moves outward. So you can have asteroids we see impact craters which are resulting from impacts from asteroids all over the solar system. So you see those on Mars, you see them on the icy satellites of Jupiter. Everywhere that we look that has a solid surface, we can see evidence of asteroid impacts. And we know that Jupiter's been hit because we can see impact flashes from when comets go into Jupiter as well. So the whole aspect of impact, asteroid and comet impacts, it happens all over the solar system.
So very interesting and fascinating. And that was actually based on a comment from one of our solar system ambassadors. So with that, it is a little bit half past the top of the hour. And so to be sensitive of everyone's time, including yours, Paul, I'd like to bring this to a close. But first of all, I want to say to all our participants out there, thank you so much for engaging with us, answering the questions in such a thoughtful manner that Paul put out there for you all to give some input on, for your valuable questions, and for your time. We so very much appreciate you joining us. And I also want to give special thanks to Rosina, Kim, and Suzanne, who have been helping and monitoring in the chat and the Q&A area. But perhaps most importantly, I want to thank you, Paul. Thank you for sharing again the knowledge, the excitement, and the passion you have for this work. We are so excited and now prepared to think about the DART mission, what will happen, and we sure hope that folks join us for the our webinar in October on post-impact and any lessons that get learned that you'll be able to share with that. So I'll give the last word to you, Paul, before we officially then bring this to a close. Any last remarks, Paul?
I'm just going to say thanks everybody for joining. This is a really exciting time. This is humanity's first planetary defense test mission. It's going to be a great event. So please stay tuned. September 26th, 7:14 p.m. Eastern Daylight Time. Watch all the social media from NASA, YouTube, and also the NASA TV. It's going to be a great event. I'll be there actually at the Applied Physics Laboratory near their mission control and celebrating and watching what happens. So feel free to join us and cheer on DART. It's going to be a great day. Thank you very much.